All right, so this is doing a concrete, such as it is, example. Get ready for some number crunching. All right. Hello. So in this video, we're going to be calculating an upper and lower sum, rather explicitly with an explicitly given function. So I have the question prompt written up here. So I have written, let Pn be a uniformly distributed partition of points x0 through xn over the interval 0, 4. Consider this function f of x, x squared plus 2x plus 1. And we want to calculate the upper sum, right, for that given Pn of f and the lower sum respectively. So as a quick footnote here, this phrase here, this, maybe underline it, uniformly distributed partition of points. So this is very common to see in the literature and in sort of a lot of other settings. I didn't see it much in the book that we're using right now, but I want to just draw your attention to it, and we'll go over what this means. It's really a side effect of uniform distributions in a lot of statistics, which governs a lot of other fields in science. So this shows up a lot as sort of a way of commonly partitioning something. And in fact, probably by the name you can guess that this is the same sort of partitioning method that you used in Calc 2. Okay, so right off the bat, the first thing I'm going to do is figure out what this partition actually is as concretely as I can. So uniformly distributed partition of points, this is just saying that I'm going to have exactly the same space between every point that I can here, right? So if you remember when we did this in Calc 2, we did this by taking the length of the interval, right, the b minus a, which is just 4, and dividing it by the number of points that we have, which is n points if you're counting these as both endpoints, right? So I'm making it into n rectangles because x0 is 0 and x4 should be, xn should be 4. So technically there's n plus 1 points here, but I'm actually making n rectangles, so I'm going to cut it into n pieces, okay? So that means really my partition, my Pn, my first point is going to be 0. My next point is going to be the length 4 over n. My next one is going to be 2 of those, because I'm going to go over 1, then another one, so I'm going to have 2 times 4 over n. And that pattern's going to keep going until I am 1 shy of the end, which means I will have done n minus 1 iterations of this. And then my nth iteration. So obviously we can clean this up a bunch. So cleaning this up, I'm going to make this, still I have 0 as my starting point, 4 over n, that's pretty self-explanatory. I have twice as much, so that's going to be 8 over n. I'll do one more just to make it clear, that's 12 over n. The n minus 1 version, I can do this as either n minus 1 times 4 all over n, or I can do it as n times 4 over n to cancel, and then minus 1 of those. So I'm going to write this as 4 minus 1 iteration, minus 4 over n. And then my last one, these cancel, and I get 4. Okay, so this is the sort of most concrete I can make this particular partition. And I'll point out just as a side note here, which isn't important for our computation, but just to make it consistent here, I'll point out that this is really the A, and this is really the B, just like we talked about before, right? Where I did 0 to 4. Okay. So, excuse me. I'll also just, point out that this is also, I can also write this, because I'm going to use this as a reference later, as x0, x1, x2 to xn, right? Because that's how they were originally given, right? x0 through xn. So I'll just point out that this is the sort of correspondence. x0 is 0, x1 is 4 over n, x2 is 8 over n, etc. xn is 4. Okay? All right. So I have the partition. Now the next thing I'm going to need to do is figure out, right, if we remember so I'll start with u. So if I'm going to calculate u of Pn f, well, I know what this is just from the definition, right? So this is the sum of k through 1 through n, right? Because there are n rectangles. That's what we were discussing before. And then we have the width of each rectangle, which is the xk minus 1 times the the sort of proper height to choose, right? The largest y value in each individual rectangle. And we called that thing capital M sub k of f. You could even call it capital M sub k of Pn of f, but this should be clear which m we're talking about here, right? So now we're sort of in a little bit of trouble. I mean, not too bad, but we can say, okay, this is still true, k equals 1 to n. This we can figure out because we've done a uniformly distributed partition, and this is sort of the virtue of uniformly distributed partition, is that this xk minus 1, the distance between any two of these is exactly the same always. In particular, it is 4 over n. But here comes the rub. How do we know the highest point of a given rectangle? And really, this usually is the problem, unless you're taking arbitrary partitions, in which case both of these things can be the problem. But we have a little luck here, because if we think for a second back at this function, x squared plus 2x plus 1, that's really x plus 1 squared, right? So this thing, this f of x, and I'll draw it sort of just right here, is the parabola x squared, but it's shifted to the left 1. So it's going to be over here, right? And our interval starts at 0 and goes to wherever, 4. Importantly then, I'm going to note that the segment that I'm caring about, this 0 to 4 segment, is a strictly increasing function. This is the thing that I care about. So it is strictly increasing on 0 to 4. Not to say that the function's always strictly increasing, but it's strictly increasing on the part I care about. Okay? But if it's strictly increasing, that means the more right I go, the higher up I get, which means that my highest point will always be the rightmost point, right? Which, if we remember, is going to be the f of x sub k, because I'm looking at the interval between the k minus 1 and the kth x term. So this is really going to be f of x sub k. Okay? All right. So again, I can keep my beginning part the same. 1 to n, 4 over n. Now, what on earth is f of x sub k? Well, for the kth rectangle, where am I? So when k is, say, 1, then I'm going to be here, right? I start at this point. And then when k is 2, I get this point. When k is 3, I get that point. So I have however much the width is, 4 over n, times whichever rectangle I'm on. So for the kth rectangle, I'm going to have, so this is, remember, just the x value itself, not the f of x value. Excuse me. The x sub k value is going to be k times the 4 over n, right? Because, right, I'm taking the right-handmost of the two, right? So this is the first rectangle, this is the second rectangle, third rectangle. So if I took the third rectangle, I'd have 3 times 4 over n. So I'd use 12 over n as my x value. Okay? So now I have a concrete, such as I can, x value here. I have something that I can plug into my f. So that's exactly what I'm going to do then. Okay? This thing does not depend on k, right? It depends on n, but n is the top thing, not the iterating variable. So this doesn't depend on k, so I can pull it out. So I'm going to have 4 over n on the outside. K equals 1 to n. And then I have f of k times 4 over n. So I take the first one, I square it. So I'm going to have this thing squared. So I'm going to do that sort of term in term. So I'm going to have 16, so right, 4 squared over n squared. So I'm going to have 16 over n squared times k squared. Then plus, but these are finite sums. So really, just to save myself some board space here, I'm going to split my sum as I go. So this is going to be k equals 1 to n. So then I'm going to have this plugged into the second piece, which gives me 2 times this thing, which is going to be 4 over n times k. And then finally, right, so this was the 2x part. So then I have plus 1. Okay. So now I'm going to distribute the 4n and pull out everything that isn't a k. So I should have just sums of k to powers and then some weird thing in front. That's my next goal. So here I'm going to pull out the 16 over n squared, multiply by the 4 over n. This will give me 64 over n cubed times the sum k equals 1 to n of k squared. Right, because 16 over n squared, this doesn't depend on k, right? Doesn't depend on the iterating variable, so I can pull it out. Same idea here, right? Remember, I'm going to distribute this 4 over n to each piece. So I have 4 over n from here, and I'm going to have 2 times 4 over n that I'm pulling out. So I'm going to have 2 times 4 times 4, so that's 32 over an n in the bottom from there, n in the bottom from there, so that's n squared, leaving me with just k equals 1 to n of k for the inside. And last but not least, this thing, I'm just going to have the 4 over n come in. And if you remember, the sum of just 1, k equals 1 to n, is just going to be n ones added together, so this is just going to be n. Okay? So now's the fun part. Now I have to deal with the sum of k squared and the sum of k. So these are both formulas from calculus that you should have learned at some point. You may or may not remember them offhand. So for the k squared bit, maybe I'll write that off to the side over here as a note. So the sum for k squared, k equals 1 to n. So this is going to be k times 2k plus 1 times k plus 1 all over 6. And the sum k equals 1 to n of k. This is k times k plus 1 over 2. Okay, so these are formulas that you should know, or at least make a note of here for use later. And they were something from calculus back in the day, although you may not have used them much since then. So that's exactly what I'm going to use here. So substituting this thing for that, I'm going to have 64 over n cubed times, so I totally messed that up, sorry. These aren't k's. The whole point is to get rid of k, right? So these are actually supposed to be n's everywhere. I just was on autopilot clearly. So let me fix all these. Surprisingly hard to erase some of this. There we go. So let me fix that. So this is n, 2n plus 1, n plus 1. This is n and n plus 1. There we go. Sorry about that. All right, so this is n times 2n plus 1 times n plus 1 all over 6. Here I have 32 over n squared times this bit times n plus 1 over 2. And here the two n's cancel, so I just have plus 4. Okay? And I can clean this up if I want. It's sort of a nice thing to at least clean up the individual terms. You could find a common term. I wouldn't bother. But you should probably at least clean up the individual terms. Here I have a common factor of 2 and a common factor of n, so I can get rid of some of that. So I'm going to have, let's see, 32 times 2n plus 1, n plus 1, all over, so I have a 3 left there and an n squared left there. All right, so that was canceling one of the n's and one of the 2's. Same deal here, I can cancel that 2 and one of those n's, so I'm going to have 16 n plus 1 over n. So that's one of those n's and that 2. And then I have plus 4. And personally speaking, I'd say that's good enough. Okay. So this is my upper approximation for Pn, the uniformly distributed partition of points. For that f is this mess. So I want to stress this is absolutely a thing you need to know how to do. You definitely want to be able to compute this thing like we did right here. That being said, as you can tell, it's kind of a mess and really annoying, so we will be trying to find better ways of doing this. A lot of the times, there are good ways of avoiding having to do this sort of bare knuckle, hard computation, but not always. So you definitely need to know how to do this, but our goal eventually in this course is to avoid doing this as much as possible, okay? All right. So that's calculating the u. I'm going to do the L next, but obviously I'm out of room, so I'm going to do some editing magic here and erase all of the u. I'm going to need these formulas again. I'm probably going to need more space than I have, so I might move these over here and get rid of this so I have some more space as well. All right? And yeah, okay. So, abracadabra. Dying over here. All right, so we want some n of k squared is n times 2n plus 1 1 n plus 1 over 6, and the sum k equals 1 to n of k n times n plus 1 over 2. And we're back. All right, so next up, our goal is to calculate L Pn of f. Now this is going to be very similar, but with a slight wrinkle. So again, we have that this is, just by straight up definition, this is k equals 1 to n of the xk minus 1, which is the same value, right? It's the width of the rectangle, but they're the same rectangles. So I'm just going to go ahead and write this as 4 over n, as we figured out last time. But now we have the little m sub k of f. And remember, the little m sub k, that is the smallest y value that we can use, right? It's the min on that rectangle. But again, because this was, as we saw before, a strictly increasing function, the max is on the right. For the same logic, we have that the min is on the left. So this is actually going to be, in fact, I'll write it right here. This is actually going to be the sum, k equals 1 to n, 4 over n. So this is really going to be f of x sub k minus 1, right, the left side. So the right side, right, was the how many rectangles we were doing, the kth rectangle, and it was k of these 4 over n's to the side. So the first one had, this is for capital M, had the 4 over n height, then the second one had the 8 over n height. So now when we're doing the min, we want back one. So the first one's going to have a height of 0, then the second one will have the second term, etc. All right? So there's a number of ways I could write this. The way I'm going to write this, so I'm going to pull out the 4 over n again, just because it's easier that way. So again, I'm only talking about the x value itself. This is often a place where where calculating this can go wrong, which is why I'm emphasizing it. Sometimes it's so hard to figure out what the x value is that when people finally get it, it feels like they computed some stuff, and so they just put it here instead of having f of that thing. And then, as you would predict, everything goes horribly wrong. So make sure that you're sort of keeping track. As hard as it might be to find, I've only found the x value. So I still have f of that thing. Usually it's not so bad once you have it to apply f, but you got to remember to, right? So here, for the kth rectangle, I'm going to have a value of, so I want to have 0 for the first one, 4 over n for the second one, etc. So I'm going to have 4 over n times, and it's not k, because at 1 that would give me 4 over n, but rather k minus 1, so that I'm one step behind, right? So this is k minus 1. And I can check, too. For the first rectangle, I should get 0. Well, k minus 1 is 0. 0 times 4 over n. That worked, right? For the second rectangle, I should get 4 over n. So 2 minus 1 is 1. 1 times 4 over n. That worked, right? So I could check a few of these if I'm not sure, make sure it works. Okay? And now I can actually apply f to get, right, apply f to this thing and actually get the expanded version. Just like last time, I'm going to break apart the sum as I go, okay? So I'm going to need more space, so I'm going to start way over here. So this is 4 over n times the sum k goes from 1 to n. So the first term, so to be clear, it's 4 over n times all of these things coming up. The first term is x squared. So I'm going to have this thing squared. And just like before, I'm going to do that piece in piece. So I have 16 over n squared times k minus 1 squared. Okay. Now, I'm going to have plus, so I'm going to have another sum here, k equals 1 to n, of 2 times the x term. So 2 times 4 over n times k minus 1. And then last but not least, I'm going to have the sum k equals 1 to n of just 1. Okay? All right. Now, I could proceed from here, and there's sort of nothing wrong trying to do that. But, as it turns out, it will be easier on myself if I do a little substitution here, because I'm noticing that I have a lot of k minus 1s showing up because I had it here. In fact, the substitution I'm going to make, I could have done here, but I wanted to point out the reason why for this line. So what I can do is, instead of continuing straight from here, I could do a substitution where I'm going to say, okay, so sort of off to the side here, a little box. I'm going to say let I be k minus 1. So what that's going to do for me is I'm going to have, so 4 over n times. So here I had k equals 1. So if k is 1, 1 minus 1 is 0. So I should have I equals 0. But I'm not going to go to n because I'm only iterating, right, n times. If this goes down 1, that also goes down 1. So I'm going to have n minus 1, right? Because this would be k equals n. That's the shorthand for that. And if k equals n, then I equals n minus 1, right? Then I have 16 over n squared. But now I is k minus 1, so I have just times I squared. I'm using I as a common index, not I as in the complex number, just to be clear, right? So this is just the index squared. Same idea here. So I have the sum. Again, k equals 1 becomes I equals 0 to n minus 1. I'm going to have 8 over n I. And here, there's no real reason to do it one way or the other, and there's no reason I have to do it everywhere. So I could just as easily lead this if I wanted to as k equals 1 to n 1. Generally speaking, it's good form to be consistent, but I'm just wanting to point out that I don't have to be. If there's some reason not to be, which here this is a nice easy computation, I can leave it that way. But now, if you sort of flip back in your notes or go back in the stuff that we've done, right, in the video, you can see this is almost exactly what we just did. The only difference is that in the other version we had 1 to n, not 0 to n minus 1, meaning that I'm going to get the same coefficient in the front, so I'm going to get 64 over n cubed here. And I'm still going to have the sum of I squared, which earlier in the video we had k squared, but it's a sum of things squared. Only now, the only difference is that it's 0 to n minus 1. Now I'll point out that the 0, if I plug in 0, it does nothing. So really, I could just as easily write this as I equals 1 to n minus 1. I didn't do that because I don't want to add confusion, right? I want to make it clear how I got 0 instead of adding the extra step. But I'm mentioning that because if I did that, in fact, so let me maybe write that here just to show you. If I do that, right, because those really are equal, because adding 0 squared does nothing, so I can really start at 1 anyway, then really I have exactly what I had before. The only difference is I'm ending at n minus 1 instead of n. But everything else is the same. All the coefficients are the same, the starting point's the same, the thing I'm summing is the same. The only difference is where I end, right? So I'm going to keep sort of going with this idea. So here I have 4 over n, 8 over n. This is 32 over n squared, just like it was before. Sum, again, I can start at 1 instead of 0, because if I plug in 0, I'm getting the sum of 0 plus stuff, right? That's not contributing anything. So that's 1 to n minus 1 of I. And finally here, this is still 4 over n times n, right? Because I'm distributing the 4 over n, and this is just n by itself. So just like last time, I can use the same formula, only now I have to be a little careful because instead of going to n, I'm going to n minus 1. So everywhere in my formula where I have an n, I'm going to plug in n minus 1. And that's especially important here because it's not that I'm taking the term and subtracting 1, I'm doing it to the n. So it has to be 2 times n minus 1 plus 1, and that makes a difference, right? So I'm going to kneel down here so I can actually write legibly. So I'm going to have 64 over n cubed times. So here I'm going to have, according to this formula, n minus 1, right, that's where the n was, times 2 times n minus 1 plus 1 times n minus 1 plus 1 all over 6. Okay? Plus, so that was just this piece. Now I'm going to do this piece. So this is 32 over n squared times. So again, adding n minus 1 in, I'm going to have n minus 1 times n minus 1 plus 1 all over 2. And finally this term, the 4 over n and n, the n's cancel, so I have just plus 4. Now it really would be good to sort of clean this up because now it's really a mess, right? So this is, let's see, this is going to be n, right? Because I have n minus 1 plus 1. So I can cancel an n and an n, a 2 and a 2. So again, I'm going to have 32. So this is canceling one of those 2's. N minus 1. 2 times n minus 2 plus 1. So I'm going to have 2n minus 1. This n canceled that n, one of those n's. So I have still 3n squared. Okay? Similarly over here, I'm going to have n minus 1 plus 1, right? So that's still just n, which will cancel one of those n's. 32 and 2, so the 2 will cancel some, so I'll have 16 n minus 1 over. That 2 goes away, that n cancels one n, I'll have n there, and then plus 4. And once again, I would say that is sufficiently simplified, okay? So again, I want to stress, absolutely, you do need to know how to do this sort of bare-handed number crunching, as unpleasant as it is to get through this process, because there are simply examples that you will have to do where you can't do it a different way, okay? But recognize the fact that doing it this way is a lot of number crunching, and as math people, we don't want to do that. We want to have nice, elegant solutions that avoid us having to do work. That's what we are all about, laziness. Embrace the laziness. So we will find ways of doing, sort of skipping this when we can, but that won't always be the case, okay? So that is computing the U and L, the upper estimate and the lower estimate. It might be worth taking a look at the two and seeing how they compare. Recall, right, that our goal with the upper and lower is that we know we have a good estimate if we can get these things close together. So think about that and think about how you might get these things close together, and then see if you're right. Do the thing you're thinking of and see if you get sort of the same number in both cases or something close together. See what you can think of, okay? And that's it.